Okay, so now we're going to do the same problem essentially again, just with a different configuration of materials for the film. So now I've got a soap film on top of a glass plate. So I've got a layer of soap on top of a glass plate. So I've got n equals 1.33 for the glass plate, n equals for the film, 1.52 for the glass plate, and then we start off in air, which has n equals 1. So I've got my two rays of light. One bounces off the top of the soap. The other one bounces off the bottom of the soap, which means the top of the glass. So we need to know what's the wavelength change on reflection. So remember, if it goes from a low to a high, that's a hard reflection. It has a wavelength change of half a wavelength. So I've got n equals 1 to n equals 1.33 for the blue one. So that's going to be hard. That's going to be a lambda over 2 shift. For the green ray, it goes from 1.33 to 1.52. So that's also going from a low to a high. So it's going to be a lambda over 2. So the net shift, since they both shift the same amount, the net shift is 0. So the two wavelength shifts cancel each other out. You'd have the same thing if you had two soft ones, the net shift would be 0. So it's only if you have one of them soft and the other one hard that you have a wavelength shift of half a wavelength. So now our equation, remember it says it's constructive, so we're going to say m lambda equals delta L plus 0 or lambda over 2. And now we know that since they cancel out, we're going to choose 0. So m lambda is equal to delta L, and delta L is, just like we had before, 2Tn, where n is the index for the film, and the film is soap again, so it's 1.33 again. Right, so now it's easy for us to find our lambda, right? Our lambda is just 2Tn over m. So that's 2 times, now the thickness is 792 nanometers. Index of refraction, we're still soap, so it's 1.33 divided by m. If I multiply all those numbers on top, I get 2106.72 divided by m. So I'm going to do just the same things that I did for the previous problem and try and find wavelengths, m values for which the wavelengths are between 350 and 700 nanometers. All right, so I can't put an m equals 0. If I put an m equals 0, I'm going to get an infinite wavelength, right? I can't divide by 0. So let's start off with m equals 1. Lambda 1 is 2106.72 divided by 1, so that's 2106.72. All right, so that's not in the right wavelength range. M equals 2. We're going to divide by 2. 1053.4 nanometers. That's still higher than the visible range. Remember, we're looking for numbers between 350 to 700 or 750-ish. Okay, so it's a little fuzzy. It depends on each individual person what's actually visible and what's not visible. Okay, so this one gives us 702.2 nanometers. So we'll say that one's visible. That's just a very red. M equals 4. I'm going to divide by 4. So we've got basically 2,000 divided by 4. So we should get something like 500. So that one's visible. All right, that'll be a green. M equals 5. So we got 2106.72 over 5. I get 421 nanometers. So that one's also visible. M equals 6. Divide by 6, I get 351.1 nanometers. Sort of. Okay, so now this is at the bottom. All right, so if I go to any higher values for lambda, I'm going to be going below the visible wavelength. Any lower values than 3 or above. So basically these are the limits of the wavelengths that I can see.